The topic in this section is the chain rule. The chain rule is very important when calculating the derivative. Up to today you learned the product rule and the quotient rule. So these are related with the product of two functions and the quotient of the two functions. And the chain rule is related with the composition function. Actually, the word chain in the name chain rule comes from the fact that a function formed by composition involves a chain of functions. In other words, a function of a function. For example, m of x is the function x squared plus 4 to the power 3. Okay, so this function is a combination of the quadratic function x squared plus 4 and the cubic function. For example, let's use the u. F of u is u to power 3, and g of, let's say this is y. So m of x equals y. So u equals g of x, which is x squared plus 4. Okay. So if you consider the combination of the composition of these two functions as the following form: y equals f of u, u is g of x. So in the u we write x squared plus 4. So we obtain x squared plus 4 to power cube. So the m of x, this function is exactly m of x. M of x is the composition of the two functions f and g. So the chain rule enables us to compute the derivative of composition function in terms of the derivative of the functions making up the composition. Okay, so when we calculate the derivative of the m of x, this is f composition g of x derivative. So we can write this derivative by using the derivative of the f and g. In this section, I will give the review for the composition function briefly and introduce the chain rule by means of a special case known as the general power rule, and discuss the chain rule itself. Okay, so we will be able to calculate this one. So first of all, let's talk about the composition rule. Composition function, not rule, composition function. So a function m is a composition of the function f and g if m of x equals f of g of x, like the example I wrote here. Okay, so here maybe briefly I can give that figure to you. The domain of the m is the set of the all number x such that x in the domain of the g and g of x in the domain of f. For example, this is the domain of the f, domain of domain of g. So the function for any point here mapping to the another value, this is the range of the g, range of the function g. Okay, but the domain of the f can be different than the range of the g. So by considering the intersection of these 2 points, this is the domain of the g. Black one is the domain of the g. I will write range of f. This is domain of g. Okay, so any point in the domain of the g can be found or can be shown here. Okay, this is the g of x. But we will focus on the some point whose image under the mapping f is in the intersection of this domain, okay, here. Intersection of the range of the f and the domain of the g. So, for such point, let's note this x instead of the x u, first of all. This is g of u. And for the point x in this set, this is g of x here, g of x. And under the mapping f, in general, actually, for any point here, you can find the, sorry, I confused here. This is the range of the g. This is the domain of the f. I'm sorry. So, for any point, we can map that point to the f. So for this point x, I don't write, okay. So, but because we focused on our point x, so g of x is mapping to the some point under the map f, okay. So this point is f of g of x. Maybe we can show that for arbitrary point x, this is f of x, okay. So, the set of the point, all points in this part of the domain of G, okay, who is image in the intersection of the range of the f and the domain of the G. So, that points are the range of the M. So, this is the range of the range of M. And this set is domain of M. But in general, the last set is the range of the function f. So this is the idea behind the composition function. Now we can turn back our problem, this one. So for this function, you can calculate the derivative for the function, and you can calculate the derivative by calculating your polynomial m of x equals, what is the x squared plus 4 cube, x squared plus 4 cube. Okay, you can calculate by this way: x squared cube plus 3 times x squared times 4 plus 3 times x squared times 4 squared plus 4 cube, okay. So this is the equivalent. So from here you can calculate, actually this is x to power 6 plus 12x to power 4 plus 60 times 3, 8, 48x squared plus 64, okay. Then easily you can say that derivative of the m of x equals 6x to power 5 plus 12 times 4 times x to power 3, 48 times 2 times x, and derivative of 64 is 0. So that is correct. But in general, if the power of this function, for example, if the power of this function is bigger than the 3, for example, if m of x were x squared plus 2022, okay, you cannot calculate your polynomial. So you cannot find the derivative of the m by this way. So we have a general power rule according to this effect. So let's write as a theorem. General. This is the special form of the chain rule. Okay, it's general power rule. I will give the generalization as a chain rule. So if y equals f of x, this is in the following form: u of x to power n form. Derivative of the f of x is n times u of x to power n minus 1 times derivative of the inside function. Actually here we calculate first of all derivative of something to power n times something to power n minus 1, okay, and by derivative of the inside function. So this is called the chain rule, okay. If we apply this rule for the m of x function, so derivative of the m of x is 3 times x squared plus 4 to power 2 times derivative of the x squared plus 4, okay, derivative of the x squared plus 4. So this is 2x. So as you see, this is easily you can calculate that derivative. Also, now you can calculate the derivative of the this function, okay, x squared plus 4 to power 2022. This seems different, but if you calculate, you can verify these are the same, okay. Let's calculate and observe this fact. 3 times x to power 4, 8x squared plus 16 times 2x. So we have 6x to power 5. 6 times 8x squared, 48. X to power 3. Actually, this is 48. And 6 times 16. That's 6 times 16. Okay, there is no problem. So this is 96 times 6, 96, yes. 96x. Okay. As you see, these are the same. So this is 96. Now you can calculate this derivative easily. Derivative of the m of x is 2022 times x squared plus 4 to power 2021 times derivative of the x squared plus 4, which is 2x. This is special form of the chain rule. So the chain rule theorem is the generalization of the power rule, okay, general power rule. This is important in my opinion. The chain rule is very important. So if m of x, let's use the black color, if m of x is the function a, external function, of e of x, integral function, okay, is a composition function. So m of x is a composition function of the e and I. Okay, then derivative of the m equals derivative of the external function, inside is the same, of interior function, times derivative of the interior function, okay. So this is the chain rule. But if of course all derivative exist, derivative of the a at the point I of x and derivative of the I of x exist. We have some other notation here. We sometimes we denote the dy over dx. Okay, here y is the e to power u and u is I of x. Okay, this is the same. So totally y is the m of x. This implies y equals m of x. So derivative of the y with respect to x equals derivative of the y with respect to u times derivative of the u with respect to x. Okay, here you should be careful because derivative of the y with respect to u, this derivative of the a, that's right, but at the point u. Okay, so what is u? U is I of x, and derivative of u of x is the derivative of the I with respect to x. Okay, so we obtain the same result with the different notation. You can apply the chain rule for any function. Okay, for example, I will not solve this question in the problem solving hour. We can solve e to power x squared plus x plus 1 function. if you want to calculate this derivative, you can calculate easily. Or ln x square plus 1. Also, we know derivative of trigonometric functions, so you can apply that one. I mean sine x square plus 1, for example, or y equals sine ln x, etc. Okay, you can apply that rule for any composition of the functions.